Hello, everyone. My name is Utsaw Siwakoti, and you can also call me Mike. And I'm here with Priyesh Shrestha to present about optical flow method for liveness detection. So as we already know face recognition systems and how it works from our previous presenters who beautifully describe how face recognition system works. However, in our part, we are dealing more with video face recognition system rather than only a picture format. So basically, let me talk about how important the detection part is in the face recognition system. So face detection here means the camera is simply trying to find the faces in the field of view, in its field of view. So most of the faces in front of the camera aren't always live people. So there might be images from different advertisement boards or signages, or there might be like pictures of people in your t-shirt or something. So it is very important for the system or the computer to which can distinguish between real faces and fake ones. So liveness detection is there to make sure that the faces that the system sees are real people or a real person. So why is liveness detection important? As you already know, face recognition system can be used in many fields. For example, to use like access controls, or law and enforcement used to use that to track people or recognize people. It can be used for greeting people in different events and organizations. For example, ISL in collaboration with Baxter's, we have developed two products called Smart Reception and Smart Attendance. So Smart Reception is a system which uses face recognition system to greet CEO or managers in big events or companies, greet them. And Smart Attendance is an attendance system for employees. So particularly, it's very sensitive in this part of the application, such as like the access control that I talk about, or the law and enforcement. Liveness is very important in this, because we want to make sure that the data we are dealing with is real, the real data or the real person is in front of that. So because most of the facial recognition algorithms, they suffer from spoofing. So spoofing here means trying to trick the computer into seeing what it wants to see, but actually it's not there. For example, holding a photo in front of you, in front of the camera, so that the camera is like tricked to see like the other person, not you, basically. So this is spoofing. So we want it to, the system to be able to detect fake or non-real faces, basically. So there are multiple approaches for liveness detection, and some of it we have achieved success in ISL. So basically, the first one is heuristic-based algorithms. So these are just a set of algorithms which are there to track the eye movement or the lip movement or the blink detection. So basically here we have been working on the eye blink detection, so that we can know if it's a fake or a real person, because normally images, they don't blink. So for optical flow algorithms, mainly examines the difference and properties of the movement of three-dimensional objects and 2D planes with respect to light, hence the name optical flow. So there are other methods to liveness detection as well, as in point number 3, such as texture, frequency, or focus analysis of images using machine learning, or use of sensors such as IR or dot projectors, which is an Apple proprietary product used in iPhones for Face ID. So these are the different kinds of liveness detection that's going on in our current world. And now Priyesh, my other colleague, is going to discuss further on how blink detection and optical flow contributes to liveness detection for face recognition systems.
Thank you. So basically blink detection. So one of the simplest concepts to differentiate between a spoof or a live person is that a real person will blink, right? So it's as simple as that. If we see an eye blink, we classify it as a live person, and if we don't see an eye blink, we know that it's a spoof or a fake image. So we take that concept and then we apply it in practice. So how do we do it? First of all, the first step is to detect the face, right? We detect faces in each frame generated by the webcam. Second step is determine if the eye has blinked. For each detected face, we classify whether the face has open eyes or the face has closed eyes. And then what we do is at some point, if it was detected that the eye were open, then closed, and then open, right? In that pattern, we conclude that the person has blinked. And then if we detect a blink, we classify that it's a live person and not a spoof. So going a little bit deeper, we'll talk about how it works. First of all, let me talk about how we do the classification, right? We need to have a model to classify if it's an open eye or a closed eye. So what we do is we take data sets, a lot of data sets of basically two classes. One is like data sets of open eye people and the data set of closed eye people. We feed them into a simple convolutional neural network. And because we need two results, right? Two classes of results. Basically, we need our model to detect if a detected face has an open eye or closed eye. We use binary classification, and then we train the model until its prediction is very accurate. And after we train the model, after the model has been trained, now we take that model. First of all, now we see the blink detection as a whole, right? So we'll talk about the blink detection from start to finish. So first thing is like we detect the face, in which we use Haar cascade classification to detect a face. Once we detect a face, we take the model that we trained previously to classify whether the detected face has a closed eye or an open eye. The model will give us a prediction, and then we save the prediction in the pattern. So as long as we detect the same face is detected on the frames, we loop it over, we classify it again and again, and we save the pattern. And once we get the pattern where we can see that there is an open eye and n number of closed eyes and then an open eye, then what we do is we then conclude that we detect a blink, right? And then we classify safely that it's a live person, it's a human, basically. So here are some of the demonstrations which we tried. So first case is with a live person, right? I don't know if you can see it properly in the internet, but so you can see like when he blinks, it will classify him as a live person. Now, basically, the second thing is like anti-spoofing, right? So we put a still image. So what you can see here basically is that it's detecting the face, right? It's detecting the face, it's detecting the open eye. That's why it's one, but it's not detecting a blink. So that's why we don't classify it as an live person. Now the question is, what happens if it's a video? Right? What happens if it's a video? And as you may have guessed, of course, it doesn't perform so well because the blink detection logic is very simple, right? If it detects a blink, then we classify it as a person. So in this case, if we saw a video, spoof a video, then it fails. So so it takes us to our next topic, which is optical flow. So the concept of it is, if you have like the basic understanding of light and shadow, we know that light interacts differently on a 3D object as opposed to a 2D object, right? So so taking this difference in the flow of light in a 2D object and a 3D object, we can assume that we can be able to differentiate between a 3D object and a 2D object based on the flow of light. So that's what optical flow basically is, right? To understand it better, basically what we do with optical flow is like we input two sequences of images. Optical flow is more based on motion. So we input two sequences of image back to back, and then we will get the flow vector of the images. Now, if we take a look into how we get the flow vector of the images, basically what we do is like we take the two frames of images, and what happens is we take the sequences of frames, we compare each pixels of images And for every pixel, we come up with a 2D vector, right? That gives you the displacement and the direction of displacement, and as compared to the previous frame. So what it means, like how much the pixel have moved compared to the previous frame. So to simplify it, you can see in here example. You can see the frame. In the frame 1, we have an object, right, divided into certain pixels, and then on the frame 2, the object has moved. So as we compare frame n and n plus 1, we can get a 2D vector. In the third example, we get the optical flow, what is basically called the optical flow vector. So it has a direction and a magnitude of change. So how do we represent it? How do we represent optical flow? So basically, we use an encoding scheme that is based on color, right? Color. So color gives the direction of the motion, right? For every direction of the motion, the 4 directions, we get a different color. And the intensity of this color gives us the magnitude, like how fast is the motion or how slow is the motion. And basically, the faster it is, the more brighter it is, and the slower it is, the more lighter it is. So one of the things is like optical flow is mostly used on motion-based applications, but it is the study of not only the determination of the optical flow field itself, but also its use in estimating the 3-dimensional nature of objects, right? 3D motion of objects. In fact, humans also use this motion to estimate the depth perception in addition to lots of other cues. So what we are trying basically is to get the structure from motion, get the 3D structure from motion. So here is what we tried. This is the first case. We input the sequences of images, and then we get the basically warping. The first image is we get of warping the 2 images, and the second one is the optical calculated flow field. So as you can see here, what we are looking is the discontinuity of the flow field, right? The discontinuity of the flow field should agree with the object boundaries. So what it basically means is like, as you can see, because it is the face is on the front and the background is on the back, we can see the discontinuity of the flow field, and hence we get different colors because it represents the orientation, right? The color represents the orientation, and the intensity represents the direction. So we can make out the depth, right? It's a 3D depth. So next, we try on the print image. We feed 2 images of print, and as you can see, there is no clear sort of discontinuity of flow field in this one because it's a flat surface, right? It's a flat surface. It reflects light basically equally on most parts, and we can see it's not a there's no depth basically. And the third one is we use the phone image. Now, when we use the phone image, we mostly get nothing. It is because it is because like in the phone screen, right? In the phone screen, whatever is in the phone screen doesn't matter because the pixels on the phone screens, the brightness is constant, right? Because the brightness is constant, it doesn't matter what's playing in the video because on each frame there is no change in brightness or the movement of brightness pattern in the image. Basically, we don't get the results we get in the other examples. So as we can see from the results that we get, and as we can see, we can clearly differentiate between a 3D model and a 2D models. What we can do now is we can just basically feed the images in a SVM classifier or other neural networks to train the model to differentiate between a 3D and a 2D, so that we can get one step ahead in liveness detection. So now Mike will take over to conclude this results.
Okay, thank you, Priyesh. So now that you have figured out how optical flow works, it is more clear that this technology combined with blink detection makes reliable liveness detection for face recognition systems. You see, both technology complements each other. For example, the blink detection was doing most of the part for the liveness. But with the optical flow, we can now distinguish between three-dimensional and two-dimensional planes. So which makes it things much more simpler and easier and trustworthy. So as a result, we get a robust face recognition system where we don't have to worry about additional hardware or expenses such as like the sensors or the dot projector, IR cameras, or those kind of stuffs. So it is easy to implement and easy to use. This is just collecting some data and just train a machine learning model or a neural network model. So after that, with no extra integration required, it can seamlessly work with our current face recognition system that we have at ISL, which we built with the Baxters. So, so its main input method is just a camera, right? So no additional system sensors, which makes it non-invasive. So, for example, if you're going somewhere and there are lots of sensors or projectors that's like coming on to you, then it's like more invasive. So it's like non-invasive, less aggressive. So this was our research and results in optical flow that you just saw, and how it plays a crucial part in liveness detection for reliable face recognition systems. So here, thank you.